Hi, welcome to the calculus of bases other than E and applications. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas, El Paso and an assistant professor at Doña Ana Community College. This calculus lecture comes to us from Chapter 5 of Larson's Calculus Text, 11th edition, Section 5.5, Bases Other than E and Applications. So if A is a positive real number not equal to 1, and x is any real number, then the exponential function to the base a is denoted by a to the x and is defined by, now get this is a new definition here, a to the x is e to the natural log of a times x. Alright, so the natural log of a is the coefficient of x in the exponent of the e, but remember e and natural log, they're opposite operations, so we could do some simplification and there we get a to the x. If a is a positive real number not equal to 1, and x is any positive real number, then the logarithmic function to the base a is denoted log base a of x, and it is log base a of x equals 1 over natural log of a times the natural log of x. And this is a little more common. We've seen this in the change of base formula. We don't necessarily see it written in this way, but it is a division, right? Log base a of x can be written as natural log of x over the natural log of a. Take that quotient apart, turn it into a product, and there we go. Not your typical definitions, but with these definitions, it makes the derivatives and integrals fairly straightforward. So, let a be a positive real number not equal to 1. It's the base of an exponential function. We're going to let u be a differentiable function of x. So, the derivative of a to the x is natural log of a times a to the x. So the only thing that changes, right, the derivative of e to the x is itself e to the x. If the base is no longer e, all that changes is that we multiply by the natural log of the base in front. Same thing, if we have some action going on here, u is some function of x in our exponent, then the derivative of a to the u is natural log of a times a to the u times the derivative of the exponent. Alright, so again, the only thing that's changed from e to the x or e to the u is the natural log of the base in front. Similarly, the derivative of log base a of x is 1 over x, right? But we must also take into account that natural log of a. So 1 over natural log of a times x, and 1 over natural log of a times u times du dx for the derivative of log base a of u. And we'll say that frequently as the derivative of the inside divided by the natural log of a times the inside. For f of x equals 3 to the 2x, I'm going to let u be 2x. Then the derivative of this exponent is 2. So the derivative of 3 to the 2x is the natural log of 3 times 3 to the 2x times 2. So we saw this before. Derivative of the exponent times the original. And this time we just have to adjust it by a natural log of 3. Frequently we'll rewrite it so the 2 and the natural log of 3, all the constants are in front of the variable portion. Y equals 7 to the 4x minus 1. We have, using the chain rule, using the a to the u derivative, y prime of x will be the natural log of 7 times 7 to the 4x minus 1 times the derivative of the exponent of 4. Rewrite it just to clean it up, or you can leave it with parentheses either way. So the derivative of the exponent times the original multiplied by the natural log of the base. Y equals x times 6 to the negative 3x, product rule where x is first and 6 to the negative 3x is second. I'll have first, derivative of the second. The derivative of the exponent is negative 3. We'll take the natural log of the base, so natural log of 6, and leave a copy of the original 6 to the negative 3x. First derivative of the second plus second derivative of the first, the derivative of x is 1. And we have a 6 to the negative 3x that we can factor out if we wanted to clean it up a little bit. Enough with those exponentials, let's look at some logs. If y equals log base 3 of x squared minus 5x, we will find the derivative to be the derivative of the inside. That's 2x minus 5. I don't know why there's a 3 there. That should definitely be a 5. I know why there's a 5 there. It's because I typed it wrong. But that should definitely be a 5. Y prime is 1 over natural log of the base times the inside. That fraction multiplied by the derivative of the inside. I prefer to think of it as derivative of the inside over the inside with the denominator adjusted by the natural log of the base. Y equals log of x squared minus x. If you've watched my earlier videos, you know that the first thing I'm going to do is use log properties to separate this quotient. I don't want to deal with the quotient rule. So I'll rewrite y equals log of x squared minus 1 over x as the log of x squared minus 1 minus the log of x. Remember, base 10. If the base isn't written, it's assumed to be a base 10, so the derivative is, for this piece, the derivative of the log of x squared minus 1 is the derivative of x squared minus 1, which is 2x, over the x squared minus 1. And we adjust the denominator by the natural log of the base, so the natural log of 10. The derivative of log of x is 1 over natural log of 10 times x. All in the denominator, subtraction there. Same thing as the derivative of the natural log, only we adjust by the natural log of the base. If we want to find an equation of the tangent line to the graph of y equals 5 to the x minus 2 at the point 2, 1, we know that we have to find a derivative. An equation of a tangent line indicates that we need a slope. A slope indicates a derivative, so I find the derivative, which is the natural log of 5 times 5 to the x minus 2. Derivative of the exponent is 1, so we've taken care of it. To find the slope, we evaluate our derivative at 2. Notice, put a 2 in for x. 2 minus 2 is 0. 5 to the 0 is 1. The natural log of 5 times 1 is the natural log of 5. That is our slope. We now have y minus 1 equals m times x minus 2. Distribute on the right, and then add 1. We're going to leave this in exact form. Do not use your calculator to find a decimal approximation. We don't care. This is the exact answer. This is way better. We can use logarithmic differentiation to find dy dx for y equals x to the x minus 1. So we'll take the natural log of both sides. Natural log of y equals natural log of x to the x minus 1. If we simplify using log properties, we can move that x minus 1 in front of the natural log, the power rule, and then we can distribute. So the natural log of y equals x, natural log of x, minus the natural log of x. The derivative of the natural log of y is 1 over y dy dx, which equals the derivative of x times the natural log of x is first, derivative of the second, plus second times the derivative of the first, which is times 1. Minus the derivative of the natural log is 1 over x. X times 1 over x, that makes a 1. 1 plus the natural log of x minus 1 over x is equal to 1 over y dy dx. So to get dy dx by itself, we'll multiply both sides by y. Y is x to the x minus 1. There we have it. You could distribute if you prefer, but leaving it there is fine with me. Not only can we find derivatives with bases other than e, we can also integrate. Always remember that integration and differentiation are opposite or inverse operations. Therefore, if one operation multiplies, the other one generally divides. So, in finding the derivative of a to the x, we multiplied by the natural log of a. Here in the integral of a to the x dx, we will divide by the natural log of a. Multiply it by a to the x plus c. Once again, notice there is not an integral with a logarithm inside. That's not something we can do at this time. We can handle that with other techniques that you'll see in later calculus courses. So here we have a power function. The power function is when the variable is raised to a power. And 3 to the x is an exponential function, where x is the exponent, so x has the power, or x is the exponent. That's how we distinguish between power functions and exponential functions. The integral of x cubed, that's pretty straightforward. X to the 4th over 4, that's what we first learned when we learned some integration rules. What is integration? And the integral of 3 to the x dx is 1 over the natural log of 3 times 3 to the x plus c. That's it. If you want to write these over top of each other instead, either of these two lines, great answers. I would accept either one, and so would WebAssign. The integral of 3 minus x times 7 to the 3 minus x all squared dx. Now when making a u substitution, try to take the most complicated part. A lot of times that's inside a radical, inside a trig function, a denominator, or an exponent. It's hard to manufacture a derivative in an exponent. So we'll let u be our exponent, and we hope that the derivative takes care of the rest. Let's let u be 3 minus x all squared. Then the derivative is 2 times 3 minus x times negative 1 dx. And I could take that negative 1 and the 2, which we clearly don't have in our original integral, and move them to the other side appropriately. Negative 1/2 du is 3 minus x dx. So we have the 3 minus x and the dx taken up by negative 1/2 and du. 7 to the u. Well, that's easy. That's a negative 1/2. 1 over the natural log of 7 times 7 to the u plus c. And then we'll reverse our substitution. Minus 7 to the 3 minus x all squared, all over 2 natural log of 7 plus c. If you want to write them next to each other rather than all in a compact single quotient, that's fine. But sometimes it's nice to have it in this form as well. The integral of 2 to the sine x times cosine of x dx. Let u equal sine of x. Then du, right, what's the derivative of the sine? It's cosine of x dx. So we take u to be our exponent. That way we can rewrite our integral as the integral of 2 to the u du. Something that looks complicated, it has a little bit of trig in it, so people already just start freaking out. Let it be easy. This is the integral of 2 to the u du. I know the antiderivative of 2 to the u is 2 to the u over the natural log of 2 plus c. Replace our u with sine of x, and we have our answer. I was told by my students that they really kind of like the hints, and I'll give you a hint on this one. This is an exam question for my online classes. You may or may not get it though, because I do use a test bank. But problem similar to this is probably going to show up on your exam. So let's find the area of the region bounded by y equals 3 to the cosine x of times sine of x. Wow, I can't even read that correctly. Y equals 3 to the cosine of x times sine of x. Y equals 0, x equals 0, and x equals pi. So finding the area implies we're looking for an integral. The x values from 0 to pi gives us our limits of integration from 0 to pi, and our function 3 to the cosine of x times sine of x, it gives us our integrand. Don't forget the dx, it's always a part of our integral. So we'll let u be the cosine of x, then du is minus sine x dx. Of course we don't have the minus here, but we'll take care of it on the outside. Since this is a definite integral, we'll do substitution twice at the beginning. When x is 0, u is 1. When x is pi, cosine is negative 1. We can rewrite this integral in terms of x as a negative 1 to negative 1 integral, 3 to the u du, and we know that to be minus 3 to the u over the natural log of 3, evaluated from 1 to negative 1. We substitute a negative 1 for u, and then we substitute a positive 1 for u, simplifying along the way. Here we go. 2 negatives make a positive. This is 3 over the natural log of 3. Negative, so we'll subtract. 3 to the negative 1 will bring that 3 to the denominator, and we'll have 1 over 3 natural log of 3. Area. So, just a little bit of information for you. Where does this number e come from? E is actually from a financial formula in terms of compound interest, and it involves limits, and so we don't really tell you about it ahead of time before calculus because we don't really look into limits then, but that's exactly where e comes from, is this limit. Not going to be on any test, but it's always good to have some information. That's it. Bases other than e, differentiation, and integration. Thanks for listening.